which will be looking at the one-sided communication part. So this is a part of MPI that I'm not sure how many of you are familiar with. How many people have used MPI one-sided? Okay, excellent. How many have used one-sided programming with some other model like global arrays or co-array Fortran or UPC? Okay. That's good. So this will be something that I think is going to be important for you to be using in the next couple of years. One of the reasons why a lot of people haven't used this approach, particularly for MPI, is that a lot of the implementations have been, shall we say, below par, in some cases really awful. But we're getting more and more hardware support for this programming model, which I'll describe shortly. So the idea here is, we talked this morning about the data communication is you move the data and you do the synchronization, and they're bound together in sends and receives. So when a send completes, you know that the data has at least left your node, and you can now reuse the buffer and receive. When the receive completes, you know you've got the data. You can split those apart and describe that in two different pieces. In one piece you say, here is data that I want to move from one place to another. And separately you may want to have a way to say, now I want to make sure that those data motion operations have completed. And so this one-sided model gives you the way to describe the motion of data, not messages, between processes. You say, I'm going to take data from this array or this variable, and I'm going to put it into this location in the destination memory, or I'm going to get data from that destination or that source memory and place it into my process in some array. And so it gives you both a different way to express the communication. It has pluses and minuses. A minus is that you have to know all those things. You have to know where the data is going to go or from where you're going to get it. But if you do that, the system can implement that data motion much more easily than it can with message passing, because all it needs to do is pick up the data and move it. It doesn't need to match tags, match communicators, and so forth. And one of the nice things is that there's been a long history of research into hardware that implements just those operations. So if everything works out right, then by specifying your communication in terms of these operations, you might be specifying just what needs to be done to move the data in the hardware. So potentially lower overhead, higher bandwidths, more flexibility. So the way that MPI thinks about this is that there's a public memory region that's exposed to other processes. So other processes can put data into this memory region or read data out of this memory region. And then there's private data, which is just not exposed. So in the message passing model, it's more like that. Everything is private. When you do a receive, you sort of give temporary permission to receive data, to accept data into a particular area of memory. The one-sided model, you have a part of your memory that you say is going to be open for other processes, and as we'll see, the collection of processes is something you can define. It will come, of course, from a communicator. That memory will be available to other processes to do updates. So in MPI terms, what we do is we specify for a collection of processes the memory that's accessible to that collection of processes. So any of the processes here can access any of these bits of memory. For example, this process can take data. It can take data from its public memory, but it can also take it from its private memory and put it into process 2's public memory. It can make a request to get data out of, in this case, of process 1 or process 3. So it can, for example, it might be able to send a tiny little message to the hardware on the node that's running process 3 that says, I need a certain piece of data, certain part of the memory region that's in the public memory region, and that gets sent back, and it can get dropped into the location designated by the call on process 0. So one key thing here is that in terms of specifying the data motion, it's all done by one process. This is why it's called one-sided. So this process, in this case, this process 0, is going to say, I want to get data from process 1, I want to put data in the process 2, and I want to get data from process 3. Processes 1, 2, and 3 don't have to say anything. The whole description, and we'll see examples from the routines, the whole description of the data motion is done by just one process. But careful to say data motion, the completion of that operation may or may not require participation by the other processes, and we'll see that too. There are two major different modes, active and passive. In the active mode, all the processes still need to participate in the synchronization. In the passive, they don't even need to, the only process that needs to participate is the one issuing the calls. So if we, again, compare this to the one-sided and two-sided, we do a send here. The send may not be able to complete until the receive matches here. And so there might be some delay. In the case of one-sided, if I do a put or a get, it doesn't really matter what's going on at the target. And so one potential benefit, if you have enough hardware support, is that this communication can be handled more efficiently. It's less sensitive to coordination with your target process. I should say, there are a lot of caveats in there. Today, the quality of the one-sided operations is, as I've said, not what we might expect, but it's getting better quickly. And one of the reasons it's getting better quickly is that the MPI-2 specification for these one-sided operations was really only suitable for a small subset of the kinds of communications, computations for which you'd use this one-sided. MPI-3 provides a much richer environment which allows MPI-3 to be used instead of some non-standard but fairly popular one-sided programming environments, and that's creating enough pressure on the vendors to make the implementations efficient. And so over the next couple of years, we expect that the implementations of the one-sided will be essentially good enough to use for high performance, and in some places they already are. Okay, so as I mentioned, the advantages of the RMA operation, well, by splitting the description of the data transfer from the synchronization, it allows me to do many data transfers and use one single synchronization. If you're familiar with the real BSP model, this was a feature of the BSP model as well. Describe the communications, then you do your bulk synchronization on those communications. It's simpler in the sense that there's no tag matching. There's no message passing. There is simply take this data from here and put it over there. The source, if I'm doing a put, is described the same way you do an send. Here's, for example, an array I want to send. The destination is done as a location in that public memory, so an offset from the beginning of that public memory. So computing that offset might require a little bit of work, but once you've got it, once you know that offset, once you know the layout of the data at the target, you can just drop the data in. And the good hardware, good remote direct memory access hardware can handle all of that for you. People have been working at building hardware that also does tag matching, this is much harder. It's a much more complicated thing to do. In some cases, I mentioned this morning, matching your sends and receives is hard. That's why we do the I sends and I receives. But even setting up all the I send and I receive matching can be complex and awkward. There are some things for which one-sided operations make a lot more sense. And it's much easier to set it up, particularly if you don't know how many people are sending. So for example, if you've got some process and you're expecting to get contributions from other processes, but you don't know how many of those are, that might be a good place to use the one-sided operations. So for example, if you wanted to get some subset of processes that wanted to add in a value, there's an easy way to write that with one-sided routines. So it's much more awkward to write it with message passing. And again, if you have the right hardware, because the hardware that you need really is just doing fairly simple moves. So if you have that right hardware, this can be faster than the message passing, the send receive. On systems where the underlying hardware is basically doing message passing, then adding this on top of this, of course, is not going to help at all. And so adding one-sided routines on top of a socket-based communication, which is essentially a two-sided protocol, you're not going to get performance benefits from that. And because they're non-blocking, we'll get to this need to know that they're complete. So there is some synchronization. So again, one of the key thing of RMA is that we've separated data transfer from synchronization. We've also put all the specification on one side, but you still have to synchronize. Yes?
When you say it's non-blocking, does that also apply for the buffer on my local node? So if I do put with my local buffer, does yours, since you're saying it's non-blocking, does it mean I also have to somehow wait till I can reuse this buffer?
Yes.
Non-blocking in the sense that it's, I don't know when it gets added at the target.
No, it's non-blocking in the sense that you can't modify any of the buffer elements until that has completed. So it's like doing so for example, put, it's like doing an ISEND. So you can't modify the buffer that you're putting. So it really is non-blocking in that sense. So one of the things that was added in MPI 3 is that there's a certain mode where I can say I'm not done doing RMA, but I need some of the routines to complete. And there's a couple of different ways to do that, but that was not present in the MPI 2. Okay. So, yes?
One process can have a single window? Is that mandatory that
a process can have many windows. Right? So you create a window object, you can create another window object. And they can be in the same communicator, so you could have a bunch. In fact, the example in the life code creates two windows, two separate windows, using this first one, MPI win create, on the same communicator. Because what they are is, each one is a block of memory, so a start address and a length, but they may not be next to each other, so I can't make them into one big window, so I have to make two. So you can have a bunch, and you can have non-overlapping ones or ones that are partially overlapping in processes and so forth. Okay. So as I mentioned, MPI 1, very simple sort of model. We had MPI win create. MPI, I say MPI 1, MPI 2. MPI 3 is a significant revision of the RMA model. So the MPI 2 RMA programs, what few of them there were, still work. It's a backward compatible update. But MPI 3 added a lot of enhancements to this model, made it much more powerful. So as mentioned, the first model for creating a window is this MPI Win create. Use this if you've got some memory that you want to expose. And this is collective. It's often better to use MPI Win allocate in new programs, because what MPI Win allocate is essentially the same as MPI Win create, except that instead of you giving it the buffer, it gives you the buffer. So why is this better? Well, it gives the implementation the opportunity to choose good memory to give you. So for example, that fancy fast hardware that may do these operations automatically, it may have some restrictions on the kind of memory that it's willing to work with. It might have some alignment rules that might be fairly coarse grain alignment. For example, I want to make sure that I've got full pages and I start on a page or something like that. This gives the implementation a lot of flexibility to give you back good memory. And so if you don't care whether you allocate the memory or it allocates the memory, this will be better. There are also some other cases, since none of you seem to have done any one-sided programming, you probably never heard of symmetric allocation, but it can sometimes be convenient if all the processes agree to allocate the memory at the same virtual address, because then various sorts of computations internal to the implementation can be made much more simple. In particular, if you've got 100,000 processes and they all know that their windows are at the same virtual address, it's very easy for them to do various sorts of relative computations. Whereas if they don't know that they're at the same relative address, they may have to keep a table of all those addresses, all 100,000 of them. So this is a better one to use if you can. Then these first two routines are really good when you know what memory you want to expose when you call the Win create routine. But say I'm dynamically allocating storage. So maybe I've got lists of information and then the lists are dynamic, or maybe I'm doing an adaptive mesh refinement code and I'm dynamically creating arrays. What do I do? Well, in MPI2 time, basically I had to allocate a whole bunch of memory and then do my own internal memory allocator within that memory that I had already exposed. In MPI3, with the MPI Win create dynamic, I can create a window to which I can attach memory dynamically while the program continues to run. So with the MPI Win create dynamic, I create a window or window object that starts with no memory. And I have separate calls to attach memory to that window. And so I can attach, in fact, a collection of memory objects that are not contiguous to it. And then finally, we were thinking about this, and I mentioned, I'll say a little bit about the memory model at the end. Dealing with shared memory is quite tricky. Rusty mentioned that yesterday. I hope that you'll hear more and more about that over the next week. It sounds really nice to be able to do this, but to do it right is quite tricky. What we realize is that the RMA descriptions that we have give us some nice tools to manipulate memory that's exposed to other processes, which could, in fact, be memory that's accessible through not just the MPI put and get, but just load and store operations through the language. In other words, if I can think of this as returning to me a pointer to memory, which is really it's shared memory. It's accessible directly just by doing a reference to a variable location from some other processes. Now, this doesn't, you can't create this kind of window object for all the processes on Vesta. The limitation is that the MPI implementation can decide what's supported under the system. And what that usually is a single shared memory node. So if you've got a single chip that's cache coherent and shares memory, and you've got multiple processes running on that chip, then those processes can create this shared memory region. and use both the MPI RMA, but also just the language-specific load and store instructions to access that shared memory. So it gives you a nice way to portably access shared memory on the nodes. Okay, so what do these things look like? Well, here is create. And so we have, first, this is the address of the data that you're going to expose, and its size in bytes. And in Fortran, you have to make sure that that's an address kind integer. It can't just be a regular integer. Then there is a displacement unit. That's the sort of natural size of accesses in bytes. So for example, if you have 4-byte integers and you want to view this data area as just a big wad of integers, then a displacement unit of the size of integer, say 4 if they're 4 bytes, makes it easy, because that means that when I am specifying a displacement, a location in the target, that location will be relative to those displacement units. In other words, if I say a displacement of 1, and I've said that the displacement unit is the size of an integer, then that will be a displacement of 1 integer's size into this memory region. So if I wanted to view that, this memory region that I had exposed as an array of integers, my displacements would essentially be the same as the indices I would use on an array access. How many people have used MPI info? Okay. So in MPI 2, started to realize that occasionally you need to provide a little extra information to the implementation. So maybe some hints on how you're going to use things, or maybe some promises on how you're going to use things, so that the implementation could do a better job of the implementation. So that's what MPI info is. So you can use MPI info null as an info value. It basically says, I'm not going to tell you anything. But there are values of info that you can use there that can help the implementation perform more efficiently. That's what that one's for. Then, as I said, this is a collective call. So it's a collective over a communicator. So com world, but this could be com self if for some reason you wanted only to talk to yourself, or it could be any other communicator. And then the output is this window object. So just like the output of communicator creation gives you an MPI com, the output of MPI win create gives you an MPI win. Okay, so here's an example. Here's I allocate some memory. I create a window with that memory location. The size, displacement unit is the size of int. Again, this info null. It's going to be collective over com world. I get this win. So now, every process can access this array by using the communication routines that I haven't shown you yet. But I can do it directly without necessarily this other process having to do anything. When you're done, you free it just like you'd free a communicator. When allocate is fairly similar, except I'm not providing the buffer, I'm receiving the buffer. And so there's, instead of there being an input base pointer here, there's an output base pointer there. And this void star, of course, is this idiom. It's really not a void star. It's a void star star, except the way C works, that doesn't do what you want. But it's an output pointer. It's an output value that is a pointer. So you pass the address of the pointer that you want set. Right? It's the same thing you do with attributes for the same weird reason. Okay. And it sort of looks like this. And so here I've got a pointer to an int, and I pass the address of the pointer. And because of the way C's casting rules work, you want to say void star here. You want the type to be void star, because otherwise it'll complain. Okay. But now, the same sort of thing, except that the implementation might have provided memory that's more convenient, read faster for the implementation to work with. Create dynamic is fairly similar, just has a few arguments. You get back this window. You can, as I mentioned, you can dynamically attach data to it. And it looks like this. So there's just this info, the group of processes. You get back this window object. Then if you want to attach memory to this window object, you do when attach. So what window, the pointer, and the size. You can do multiple when attaches. Then you should detach it and then free. So again, if you were doing something where you're doing dynamic allocation, lists or trees or adaptive measure refinement, that's how you would do that. And I'm not going to talk about the shared memory right now. So, okay, yes?
Regarding the create and allocate and the difference, is there, it sounds like there is no way to map memory into MPI, or somehow, is there a full documentation of what? So what I mean is that if the communication is isolated in an application in a certain module, but the allocation happens outside of that module, then porting to MPI-3 and one-sided communication would require refactoring the entire code base. So instead, there could be something like map my memory in, or say that this memory satisfies all the needs that, including alignment, including page locking, or
yeah. So there's the dynamic, the create dynamic should probably let you do most of what you want. The specific details we should probably talk about offline. But the create dynamic gives you a fair amount of flexibility. One of the things, in fact, the displacements, the way you specify the targets for the dynamic is essentially relative to the beginning of memory. So that way it also differs from the others. So in MPI-2, as I mentioned, the MPI-2 one-sided was fairly simple. It just had 3 routines for data communication. You could get data from a remote process, you could put data to a remote process, and you could modify data in a remote process. MPI-3 added a couple of other important ones, and this is in fact not a complete list, but this covers the most important parts. So it added a get accumulate. So this accumulate only let you modify results on another process. Often, though, what you want to do is read and have that value of the remote values and then do an update. So read, modify, write is a common operation. So this is a read, then modify, write. So accumulate is just modify, write. So you modify the value and you put it back into the remote memory. There are a lot of interesting algorithms that require atomic updates, so more complex operations that have to be completed as a single unit. So for example, compare and swap is where you compare 2 values and you make a swap if the comparison is true, otherwise you don't. And a fetch and op, where you fetch the value and you make an update, and you guarantee that that's an unbreakable operation. So nobody can do a fetch while you're in the middle of doing your fetch and op. If they do a fetch, they either get the value before you did your fetch or you get the value after you did your op. Right? So for example, if I want a counter and I want everybody to have a unique counter value, fetch and op will let me do that because I can start at 0. Fetch and op is sum. So what I do is I fetch, I get back a 0, I apply the sum, I get 1. Because it's atomic, I'm guaranteed that if another person is doing a fetch and op, they're not going to get 0, they're going to get, well, they're either going to get 0 and return 1, and then I'm going to get 1 and return 2. Or, yeah, so yes, there was a...
So when we do MPI accumulate and we send the instruction, who does the actual update? The processor on the other end, or?
So that, yeah, so how does this happen? Well, it depends on what hardware you've got. So if you've got enough hardware, and it's true that even for some of these operations, some of these can be done in commodity hardware. And so you can send the data to the commodity hardware on the network, and the network will just do it. So like some of the operations are just data motion operations, so no arithmetic. In the case where you can't do that, then there has to be an agent on the remote process or remote node that takes care of the operations. So what is that agent? Well, the easiest way to have that agent is to have a separate thread that's running someplace that will receive essentially a command to do that sort of remote operation. On a thing like a BGQ, there's that 17th core. That 17th core can run that agent. On a machine without an extra core, then you might have an agent that sits around and might preempt a user thread on one of the existing cores, but only when it's needed to do one of these operations. The hope over time is that you get more and more of this in the hardware, so that agent is rarely needed, if ever. And in fact, it took a long time to get particularly these defined. And the reason that we had so much trouble defining these was we were trying to ensure that the definition that went into MPI would not stand in the way of having hardware do those operations. Right, so you might read, there's a number of constraints about the operations, the sizes. Those were there because in talking with the hardware designers, that's what they felt was going to be realistic. Okay, so Git looks like this. And in the language of the MPI RMA, we talk about the origin process and the target process. The origin process is the one that is making these calls. The target process is the victim, the process that's whose public memory in that window object is being accessed. So a Git, we pass the origin address count and data type. So that's essentially the receive buffer, because a Git is going to acquire data from someplace else. So you say where you want that data to land, just the way you would with a receive. Then there's the rank of the target, the process from which you want to get the data, the displacement, and then the number of the data type inside that window object. So that's a lot like the data you'd have on a send. If you force the send to happen at the other process, you'd have, I'm sending so many types of a current data type from some address in memory. Well, instead of saying address in memory, you have displacement from the beginning of the window, right, relative to this displacement unit. So one of the things this helps with is, well, it's a sort of virtual address. Well, first of all, I could have an MPI implementation where my process was 32 bits, but that process, the target process, was 64. So I don't even have the right type for a virtual address, but I can still manage displacements. And then second, one common error in shared memory code is to compute the address of a variable based on where it is in my process and think that that's going to be the same address in the target process. And so again, this helps avoid that problem. So the one thing again that's different is this is an address because that's where data is going to land in my process. This is a displacement. That's a location relative to the beginning of the window. Okay, and then it's, instead of being in a communicator, it's in a window. And so this does a get. Example there. Put is almost the same thing. Again, I specify where it's coming from as an address, counted data type. Think of this as sort of, that's the send part of the put. And then where it's going. And then here's the receive part of the put at the target. So again, the displacement from the beginning of the window, then the count in the data type, and the window. So both if you want to compare the RMA to send receive, each of the RMA operations essentially provides all the information of both the send and the receive. Notice that there's no tag, so there's none of this tag matching. And this moves data then from the origin to the target. And then accumulate, it's like put, but there's an MPI op. So instead of just dropping the data into the target process's window, it updates the data there according to the MPI op. And the MPI ops have to be predefined ops, like MPI sum. Why do they have to be predefined? Well, it comes to the question that was just asked. If I have a user-defined operation, how would I do that? Well, that would mean running code written for the origin process on the target process, which might not have the same instruction set, for example. So that limitation of just the predefined operations means that we know what's going to happen. It is a somewhat of a limitation, and there are people doing research looking at ways to deal with that. But for the RMA, you just have these predefined operations. Okay, so there's even another op called MPI replace, which gives you a kind of atomic put. Okay, so those three were the ones that were in MPI 2. MPI 3, as I mentioned, added a couple of other ones. The first one is this get accumulate. So again, we just have the predefined MPI ops. But in addition to doing the update, you do get the original data back. So this is a full read, modify, write. And it turns out to be quite important to be able to have read, modify, write operations. We also added a new operation. This is an MPI no op. So why do I do a get accumulate with no operation? Well, it has to do with the semantics of the memory model. So this is a forward reference. But this helps me provide what's called an atomic get. Okay. So one of the things then to understand as well, remember first, these are all non-blocking operations. Right? And there are no tags. So there's no real ordering. So for put and get, it just happens in whatever order it happens. Well, this is important for performance because if you look at modern networks, even if you do multiple puts from the same process to the same target process, the data may follow different paths through the network. And if I don't care which one arrives first, then that's pretty easy. I just allow them to arrive. If I insist that they arrive in a certain order, now I've got to keep track of when they were sent. So maybe I have to have sequence numbers on them or timestamps or something else so that I can ensure that I maintain this ordering. Okay, that should sort of sound pretty painful and complicated and expensive in terms of performance, and it is. So what the MPI RMA model does is it defines this in a way that allows systems to provide the best possible performance. So that's how MPI 2 is defined. Now, there are times, however, when it's really awkward not to have any ordering. So what we've done is the accumulate operations do allow you to specify ordering. And you can turn off the ordering. You have sort of fine-grained control of the ordering. And that allows you to get reasonably good, or allows you to give the implementation the opportunity to get good performance. Now, another thing is, one of the reasons why the ordering doesn't matter for put and get is, again, the MPI standard says that a program which has overlapping puts or overlapping gets or overlapping combinations of put and gets before you synchronize. Well, in MPI 2, that was erroneous. That meant that the program could do an MPI error and fail. Again, this was something that people just said, no, I just don't care. It's okay, it's okay if it's garbage, I just don't want it to fail. So in MPI 3, the result may be garbage, but it's not an error. It's just undefined. So it makes it risky for the user, but there are times when it makes sense. And so again, trying to define the interface to give the potential, the opportunity for the most performance, the MPI RMA has a sort of loose definition. If you need to be able to update or access the same memory location, that's what the accumulate and get accumulator for. They have well-defined semantics for it. The atomicity is defined in a certain way, so you can be guaranteed that the behavior is what you expect, at least if you read the standard. And that's one of the reasons why there's that MPI the MPI no op. So as I mentioned, we have these additional compare and swap and fetch and op. These are tricky to impossible to implement efficiently in terms of these simpler operations. And so you essentially need direct access. You need to be able to tell the system, I want to do a compare and swap, or I want to do a fetch and op. And so MPI 3 provides you access to these. And you can do some really cool things with these. Okay, so now we've talked about moving data, but you still can't use it. Because remember, all those operations are non-blocking. Even the fetch and op is non-blocking. So you need to answer these questions. And whether you're dealing with MPI or any other sort of one-sided model, you've got this question of, when can you do that read-write? So you asked, is the non-blocking routine really that non-blocking? It is. And so you have this question of when can I when can I know that the remote memory is okay? When do I know that my local, the origin buffer is okay? And so there are a number of synchronization models for this. There are a couple of different types of epochs. I mentioned sort of two categories. There's active target and passive target. So in the active target, effectively all of the processes that created that window participate in the synchronization. They didn't have to participate in the data motion, but they participate in the synchronization. In the passive target, only the process that issued the communication routines also does the synchronization routines. In the passive target case, we can also do sort of more fine-grained control through things like through these flush routines, which were also added in MPI 3. Okay, so anyways, the simplest one, this is now back to the active target synchronization. So many programs have the sort of, I have a communication phase and a computation phase. So the RMA version of this is, I start my communication phase, I define the puts or gets or whatever combination of data motions, and after I've defined all of them, I need to complete the communication phase. So then I do a synchronization. And that synchronization is easily done with a fence. Name it sort of historical. Essentially fences these memory references off from before and after the fence. Okay. So you can think of it as being sort of like a barrier. In some cases, some systems have had hardware that provided a very fast fence operation. I mentioned a really fast barrier that you can do some things. Some machines have provided a really fast fence. Okay. So one feature of MPI is you use fence to both start and complete So you do a fence, you do gets, maybe you do puts, you do another fence. When this fence completes, you know that all of the RMA operations on that window have completed both locally and remotely. So you know that your buffers, the ones defined by the origin buffer, they're all usable. So if it was a get, there's now data in there that you can look at. If it was a put, you can now deallocate it, scribble over it, whatever. Everything will be fine. And you know that the remote process has gotten any data that you put and any data that you had gotten. You know that the process can do whatever updates it wants now to that memory. There's a variation of this called post-start complete wait. Potentially, this could be more scalable in the sense that you only define the processes with whom you've exchanged data. So again, it sort of depends on what kind of hardware you have, whether this is in fact faster than using a fence. If you've got hardware for the fence, the answer is probably no. But it does allow you to specify exactly the set of processes with whom you're communicating, the ones that you have put data to, the ones that you might be receiving data from. And again, the collection of processes participates in it. So a process which is only the target of RMA operations must still participate in this. This is why it's called active target. So all the processes in the window object are active in the synchronization. The third type, the passive target, is called lock-unlock. In MPI, we almost always, I think we always have messed up some word. So we've used a very misleading term. So in MPI 1, we talked about the extent of a data type. We really should have talked about the stride because that's what it is. In MPI 2, the mistake was this one. So we call these lock-unlock. It has absolutely nothing to do with like a thread lock or a process lock. To start with, lock need not be blocking. So what are these? What they maybe should have been called is begin passive and end passive, because that's what they are. So in the lock-unlock mode, when I say lock, I say I am beginning passive target access. In other words, having called MPI win lock, I am now permitted to call data communication routines like put or get or accumulate on other processes in the same window. And when I am done making those calls and when I need those non-blocking routines to complete, I do an unlock. And when the unlock returns, I will know that all of those RMA operations that I initiated will have completed locally and remotely. So that's the important part. But the lock, for example, again, maybe non-blocking. In fact, for those interested in the latency-dominated part of the domain, you really want, well, what you want to have happen is you want lock to say, oh, goody, I'm going to make some RMA calls. That's it. And then you want to make an RMA call, and you want it to say, oh, that's a small RMA call. I wonder if there are going to be any more. And then if it gets an unlock, it can say, oh, that's it. So now it actually performs the operation, waits for the data to come back, and returns. That's the right way at the latency-dominated end to implement these things. At the bandwidth-dominated end, then the lock might want to block so that I can immediately issue these things. So again, it's exactly what is done depends on the implementation, depends on the algorithm, depends on the situation. Right? The MPI specification gives the implementation a lot of flexibility to deal with this. And in fact, implementations can be designed to do both things. So they can be designed to try to optimize for the latency side. But if they see that they've got so much data to move that it's time to get started, they can get started. So the routines look like this. You normally lock a specific rank. There are exclusive and shared locks. So you can say whether or not you would, it's okay for other processes to access the target rank's public window at the same time. So for example, if you initialized a shared data array that you want everybody to be able to read, well, maybe when you're initializing it, you do it exclusively. But when you're in a mode where everybody is just reading it, you do it in shared mode. The asserts provide a little bit of information that can be used to optimize the use of the lock and unlock. And then we've got the when object that this applies to, and then the unlock is fairly simple. When should you use these? Well, again, if you've got the right kind of hardware, the one-sided routines, if you've got the right kind of hardware and the right kind of implementation, can take advantage of using the hardware directly to do the data motion. The passive mode, the one using the when, lock, and unlock, is good when you've got, for example, irregular data exchange, so you don't know when other processes are going to need to access the data. Remember, in the active target mode, all the processes have to participate in the synchronization, which means that it's pretty easy for them to do all those puts and gets, but then they all have to agree on getting together to do the synchronization. So for a halo exchange, like the life example, it's pretty easy because you've got the halo exchange. Everybody's participating in the halo exchange. They can do puts for the halos, then they can do their fence, and they're done. If, on the other hand, I'm doing some calculation where I may want to access some data in a big table, and I may need to do it as I'm doing some other computations, then in that case, I probably want to use the passive mode because I want to simply have a process go lock, get, unlock. Okay. In fact, there's a programming system that has provided such a model for a long time called global arrays. You have a shared array, effectively shared across all the processes. You can access elements of the array or blocks of the array independent of the other processes. With the additions to the MPI RMA for RMA3, we can now implement that programming system entirely in the MPI3 RMA.